Okay. Delay for my Butterfingers. Now there's the green button, and if you press it, it's like an emergency lock. I must have pressed it and then locked myself out. It was my fault. That's what they say. Anyways, here we go. We've got our final exam date. I also posted, because everyone always wants to know, hey, what was the average? What was the average on this test? Well, the average was 65.5. But from this test especially, you know that you should actually be asking, hey, what did the distribution look like? Right? Was it a normal distribution or was it skewed? Right? You know that. And so without showing you the distribution of the grades, you can take it one step further. What if I give you the median of the grades? Median was 58%. Remembering that the mean is pulled in the direction of the tail. No. What do you think this distribution would look like? Might look something like this, where you might have the median at 58%, and then the mean pulled in the direction of the tail, 65.5%. Right? I'd consider those two percentages different, right? And so there's a little bit of a skew, but not bad. And don't worry, the skew wasn't very strong at all, but it's there. So from last day, well, any questions about the test? So how I mark the test, let's talk about that. So first, there's going to be, like I said, a little number up at the top. That's just your sorting number, so where your name is on Moodle, just so I can sort lazily, okay? And so it doesn't mean anything. Your grade's on the inside, tucked away, okay? And as promised, if this test grade is lower than test 2, right? Especially if you're not happy with this test grade, totally fine. It's a hard test, right? Test 1's always tough, okay? And so then as long as test 2 is good, and as long as you're able to show me on the final exam that you've got a good handle on this stuff now, right? Then I'll take your final exam grade and pretend that's your test 1 grade, right? And so, or if you want to think of it as shifting the weight of test 1 to the final exam, I'll do that for your lowest test grade, so just one of them, right? But so don't let it bring you down. It's going to come back up on the final exam, right? Learn from it, study from it. That's why I want you to keep your tests. On Moodle, I've posted the solutions to both of the versions, as well as blank PDF copies of each of them. Right, you'll see that they're very similar, just some different numbers, right? But the solutions are kind of in shorthand, right? Just kind of brief solutions for the most part. So if there's something that you want me to elaborate on, you can come see me and we can talk about it. And so for review, we were here. And we said that, okay, on our formula sheet, even though we tend to ignore this part of the formula sheet later on, but it is happening in the background, and so we have to talk about it at least once, which we did last day. And so p hat follows a normal distribution centered on p with a standard error. I'll just transfer the little that we got to right there. Standard error of p hat, which is the root of pq over n. Now, with that, right, from this normal distribution, P, Q, you might remember that P is the population proportion, right? And so here, recall, P is the population proportion, which we're not going to have, right? And so really our goal in this chapter and in the following chapters is going to be to figure out what P is, right? And so one of the ways that we can do that, but we don't know P, right? We're trying to learn about P. We're trying to learn about P. So one of the ways that we do that is with a confidence interval. Confidence intervals in general, right, give us a plausible range for what P might be. So a confidence interval, or I'm going to start abbreviating it just CI because it's really long to write. So a confidence interval gives a plausible range for P. We're trying to learn about P, right? And so our first step towards learning about P will be, okay, well, what's a reasonable range for what P might be? And so that's what a confidence interval does. Now, if we talk about, I'll zoom in and then I'll write it out properly, but a confidence interval we've seen before. We didn't call them confidence intervals, right? But we've seen something like this, right? Where I have my best guess at what P might be, right? P hat, that's a good guess, right? From my sample. And then we'll talk about this Z star, but in the past, what we've done is we've said, how about we just move out 2 standard deviations, right? Capture the central 95% of the curve, seems reasonable, right? And so we're going to keep it open-ended for central 95%, central 90%, 99%, right? We'll be able to adjust that. So that's why it's just a Z star. Okay? But we'll talk about that today. And then we have the standard error-ish of P hat. Okay? The P's have been replaced with P hats, again, just because that's our best guess. Okay? So all CIs have the form of a point estimate, right? Your best guess. That's going to be one thing. Plus minus, and it's kind of, plus minus some critical value times the standard error of the point estimate. The critical value is that Z star. Now, the critical value is the only thing that dictates your confidence level. And so the critical value determines the confidence level of the confidence interval. Otherwise, the point estimate is just from your sample. You only get one sample, and so that's not going to change. And from this point estimate, we'll be able to calculate the standard error of the point estimate, which is why we need this theoretical distribution, but it is showing up as we use it in our formulas on your formula sheet. Yeah? So Z star, or I should write it out here. If we have P hat plus minus Z star times the square root of P hat Q hat over N, how can I map this? My point estimate for P is P hat. So if I'm trying to build a confidence interval for P, then I use my point estimate, which is P hat. My critical value is this Z star. And then the standard error of the point estimate in this case is the standard error of P hat, which is the square root of P hat Q hat over N. And you might recall that Q hat is just 1 minus P hat. Right? Okay. So before we go any further, we'll I have this nasty habit of just doing the slides before I go through the slides. I know, it's bad. I can't help it. It's because I study them beforehand and then I just have them in here and I can just say it. But I want to link them up. So section 5.2 is confidence intervals for a proportion. And so we're going to call this a one sample proportion. I gave you that kind of roadmap last day where, okay, we start and we develop all these rules with one sample proportion. And then we graduate to, well, how about if I have two sample proportions and I want to compare those two, right? Then how do I do a confidence interval? And then how do I do a hypothesis test? Or what if I have three or more proportions? Then what do I do, right? And then the list goes on. And so we need to introduce all the rules, but then all the rules stay the same. So like I was saying, confidence intervals give us a plausible range of values for the population parameter that you're trying to learn about. And so kind of like using your point estimate or the sample statistic as your best guess. Now, that is your best guess, right? But that would be equivalent to using just a spear in murky water. Because remember, we don't know what the population proportion is, right? And so we're just trying to figure out what it is. And so we're just kind of jabbing, taking one sample, jabbing once, and that's it, right? So that's not usually that great of an estimate, but using a confidence interval is like fishing with a net, because then you say, okay, based off of this sample, I go down a little, I go up a little, and then I feel pretty good that I've captured the population proportion. And so all these fishing analogies, but if we report a point estimate, we probably won't hit the exact population parameter. I think everyone can agree that that's pretty reasonable. Of course you wouldn't, right? Because every time you collect a new sample, the sample proportion is going to change slightly, right? And so, but if we report a range of plausible values, then we start to see, okay, is this a reasonable value for P? Here's a long example that we'll refer to, so I may as well read it, but I'll do a shorthand version. Facebook's categorization of user interests. So most commercial websites collect data about their users' behaviors and use these data to deliver targeted content. If I'm the one to tell you that, I'm sorry. Recommendations and ads, but we all know that that's what's going on. Okay? And so to understand whether Americans think their lives line up with how the algorithm-driven classification system categorizes them, right? Pew Research, which is a huge research firm in the States, asked a representative sample of 850 American Facebook users. So that's going to be our population of interest. Okay. How accurately they feel the list of categories Facebook has listed for them on the page of their supposed interests actually represent them and their interests. So many interests. 67% of the respondents said that the listed categories were accurate. Okay, so 67. So let's assume that they were given two options. Yes, these are accurate for me, or no, these are not accurate for me. Okay? We're going to estimate the true proportion of American Facebook users who think the Facebook. I just think it's funnier to read it that way. Who think Facebook categorizes their interests accurately. Now, we need to snag some information, but what's nice about one sample proportions is there's not a lot of information that we need in order to answer these questions. But we are given some pieces of information here. We are told that we have a representative sample of 850 American Facebook users, making N 850. 67% of those 850 tells me that p hat is 0.67. Remembering that p hat is a proportion, and proportions and probabilities have to be between 0 and 1, right? So we often report the percentages, but we work with the decimals, right? And so 67% of the respondents said that the listed categories were accurate. And so now we're going to estimate the true proportion of American Facebook users who think Facebook categorizes their interests accurately. The true proportion, that's going to be P. Right? We want to estimate what could this thing be. And so to do that, we're going to build a confidence interval. And should I? I can't resist. Before constructing a confidence interval, we need to check the conditions for inference are satisfied. Which we introduced last day, are satisfied. Right? In order to be able to use the normal distribution, right? And I'll highlight that here, right? Otherwise, we can't assume a normal distribution. And that would be bad, because everything we're doing relies on the normal distribution. So we have to check the conditions. There are kind of two main categories for the conditions. And so there's first the independence condition, which we usually, right, as long as we have a randomly selected sample, right, then we can assume that these observations are independent of each other. In this case, They even went so far as telling us that, hey, this is a representative sample, and from this representative sample, we can assume that they're all independent of each other. And so I like to do the random still, but in this case, and I'll do it in a different color here, green maybe. Told it is a representative sample. But in general, if you've collected a random sample, you can assume that those observations are independent of each other. The next one is optional. It's the n less than 10% rule. So your sample size has to be less than 10% of the population. I think it's reasonable to assume, and usually how I phrase these things is, it is reasonable to assume that 850 Facebook users is less than, or sorry, American Facebook users is less than 10% of American Facebook users. Reasonable, right? Sold. It is reasonable to assume n equal to 850 is less than 10% of all American Facebook users. Remember the reasoning behind the n less than 10% condition? If we have too much of the population, right, especially if we're dealing with a small population, and we've picked up too many of them, right, then we're introducing non-independent observations in our sample. So that's the concern, but I'm here to tell you that's never a problem. Just go big, go as big of a sample as you can, right? So the next subcategory is the actual normality condition, or the sample size condition. I like to call it normality because then we can be reminded that, hey, if I don't check these, then I can't assume normality, right? And that's bad. What was the condition? I need my expected or observed successes greater than or equal to 10. Now that's a count of 10. Okay. How do you check that? If you have X, which is the number of successes, cool, you can just use that. Okay. But X is also N times P hat. Now, because the information that we were given was N and P hat, I'm going to go for this option here, which is 850 times 0.67. Usually, because the 67% is rounded, I'm not going to get a nice clean number, but let's try it. Which is 569.5. That's greater than or equal to 10. Great. The next one is the failures. Now, when we do 850 times 0.67, this is the observed successes. Whereas the expected successes would be if I had some idea about the population proportion. Okay, and so here in this case, we're doing the observed successes. I'm going to keep it as expected or observed just a little bit longer because we'll need it in the next section. where, surprise, surprise, we'll use the expected instead. But the observed, so the expected or the observed failures. And for confidence intervals, we use the observed. Use the observed. Right, from your sample is what I mean. From the sample. By that. And again, it has to be greater than or equal to 10. Lots of ways that you can go about it, right? You could say, well, if I have a total of 850 and 569 and a half of those are successes, then I can take those successes away and find the failures. Sure, all right. So you could say, well, n minus x, which is the same as n times q hat, which in this case is 850 times 1 minus 0.67, which I have 0.33 times 850, I get 280.5, which is greater than or equal to 10. Here's the thing about the conditions. They're always going to check out, right? Because in this course, if they didn't check out and you tell me, hey, these conditions are not met, then technically you should just not do that question, right? And so, yeah, kind of a loophole, I guess, but they'll always work out, right? And so it's our job to know to check them, but if you're finding that they're not working, then something is going wrong, right? Because they will work. Just a hoop we gotta jump through. Okay. Now, we can assume independence. Oops, we can assume independence. We can assume normality because these conditions are met. Therefore, we can now build our confidence interval finally. So let's start with the bare bones of a confidence interval. Or maybe I'll say, therefore, the conditions for inference are met. Inference are met. Or specifically a confidence interval. So in general, we have a point estimate plus minus some critical value times the standard error of the point estimate. In the specific case of P, right, we're trying to build a confidence interval for P. So a confidence interval for P is going to be P hat plus minus Z star times the square root of P hat Q hat over N. I can move this P hat closer. I don't know why it's so far out there. Let's fill in what we know and then maybe backtrack to the Z star. Huh? We know that P hat is 0.67. So here we're given that P hat is, oops, that doesn't look like a hat, is 0.67. And N is 850. That was all we were given in that problem. 0.67 plus minus, and I'm going to just keep it as a Z star for a little bit longer. Times the square root of 0.67 times 0.33, right? 1 minus 0.67 from earlier. Extend this root, divided by 850. Now we need this Z star, this critical value. Right? All we've said so far is this critical value determines the confidence level, right? And so here, Z star determines the confidence level of the confidence interval. Well, now, we were just told to estimate the true proportion, which is P, of American Facebook users who think Facebook categorizes their interests accurately, right? And so we're not told to use a specific confidence level, but most of the time, the question would read, construct a 95% confidence interval to estimate the true proportion, blah, 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 blah. Right? And so as a default confidence level, it's 95%. We use a 95% confidence level as a default. In industry, 95% is going to be your go-to confidence level. And any sort of journal that you read, Dear Diary, no, I mean scientific journal that you read, they tend to use a 95% confidence interval. Right? So what is this thing? Well, it's the thing that's relying heavily on the normal distribution. So got p hat in the center because that's our best guess at p, which is the true center of the normal distribution. But what we want to find is, okay, I want to go down a little from p hat and I want to go up a little from p hat, right? So how much is a little? Well, if we're using a 95% confidence interval, what that translates to is that we would want to force this area to be 95%. Half of you are excited, half of you are bummed. We've done this before for the same reason. We've done this before. This would be your negative version of Z, right? And here's your positive version of Z. Right? They'll be the same. By symmetry, they'll be the same. Right? So you just need to find one, and then you can find the other one. Do you remember how to, and we only need to find our Z, right? How do we do it? We want to force the central 95%, right? And so working out from the center, well, that means that from here down, I have 5%, but only half of it, because I have the other half of the 5% up here, right? And so this area is going to be 0.05 divided by 2, which is 0.025. And here I have 0.05 divided by 2, which is 0.025. Right? They'll be the same. The Z table that we're using only gives the areas to the left. But as long as you remember the symmetry, you can grab this negative version of Z, right? And you can use that as your Z star, right? Just dropping the negative essentially. Or if you want to get really crazy, plus a negative Z makes the minus part, and minus a negative Z makes the plus part, if you wanted to. Crazy. I know. You can play around with it. So how do we find this Z? Well, we can go to our Z table. It's old. And what are we zipping around for? We're looking for a table entry, right? A probability that's closest to 0.025. And you don't want to get thrown off by this 0.0025, right? You want 0.025, bigger. 0.026256. Haha, what a jackpot. It's on here, plain as day. We don't even need to find the closest value or anything, right? That's nice, because now I can snag this and bring it in here. Paste. So here we see that negative Z star is negative 1.96 from the Z table. Huh? Oh, I do want to make a note. I'll make a mention. I'll remove it later. But on the test, if you see a not equal to, I want you to pay attention to those. Okay? Because if you tell me that 0.025 is equal to negative 1.96, I know what you mean. I do. I really do. I understand what you're saying, but it's just not true. Right? And I've got a real pet peeve. People telling me things that are not true, especially in this course, right? Probably only in this course, actually, right? So don't tell me things that are untrue, right? And just be really careful. So I do make some notes in your test, right, to kind of guide you along. And so make sure you pay attention to those, right? Because I'll get meaner as it goes on. Yeah.
How would you like us to write it in the test thing?
You can write it in words, right? And so like we did in class, you would say using the Z table, we find the table entry of 0.025 corresponds to Z equal to negative 1.96. Lots of words. Or if you're comfortable mastering the shorthand, the probability that Z is less than or equal to negative 1.96 is equal to 0.025. Shorter, but harder, right? So you get to choose. Long and easy or short and hard, I don't know. It's your choice. Yeah. If you say using the Z table, fine. Fine. I don't want to see equal signs. That's my qualm. I'll just circle this. I'll keep it in here, but this is a random test note from test 1, I guess. Well, so just be careful. Okay, where were we? Oh yeah, we just cracked the code. Z star is 1.96. Right? And so our critical value is 1.96. for a 95% confidence interval. Huh? That's neat. Huh? And in the past, what were we using? We were using 2, right? From the 68, 95, 99.7 rule, you can use 2 as well. But notice that 2 is really close to 1.96, or rather 1.96 is really close to 2, right? And so for your math, I want to see you using the proper value of 1.96. And so I'll make a note here. Previously, on stat 121, previously we used Z star equal to 2 from the 68, 95, 99.7 rule. From here on, we should use the proper Z star equal to 1.96, right? But 1.96 is really close to 2, right? Okay. So, good. That was our missing piece, right? From 0.67, we have to go down and up 1.96 standard errors, right? So let's do that. I'll bring it down here. 0.67 plus minus 1.96 times the square root of 0.67 times 0.33. Put my crook on the square root too early. 850. Starting in the square root, I'm going to go 0.67 times 0.33. And I'm going to right away divide by 850. It's going to be a really small number, but I just want to check in that you've got a good handle on your calculator. So you should get 0.00026. I have to check my scientific notation here. 1, 2, 3, 4. Okay. 6, 0, 1. 176471. I know I can't resist. It's a compulsion. I see it, I write it down. It's easy. Now, as long as you remember to take the square root, right? You don't want to forget to do that. So my next step is to take the square root here, and I get a much more reasonable answer for my standard error. I get 1.96 times 0.01612816316. Okay. I want to make sure that you keep all your decimal places, right, as much as possible. And then, now that I've ditched the square root, I've taken care of it, rather, I can multiply by 1.96 because I want to find what this whole plus minus chunk is first. Times 1.96, and I get plus minus 0.0316111998. This value should be small, right? Because it's a proportion. It's just a little buffer, right? It's just my standard error. It's my spread times 1.96, right? And so it's not going to be large, but this becomes 67% plus minus 3.16%, right? Kind of reasonable. This, when we've multiplied the critical value with the standard error, we call this the margin of error. And so a lot of kind of articles, scientific journal things that you read will report the margin of error. Yeah? And so the margin of error is Z star times the standard error of p hat. This is where it's helpful to know how to store values on your calculator, right? But as long as you keep, I don't know, 4 decimal places in this case, right? Why did I choose 4? I kind of get a lot of activity and I get a lot of information out of 0.0316 if I consider rounding, right? If I round at 1 decimal place, well, that's bad. There's no information there, right? 2 decimal places, I can see that it's followed by a 1, which would be rounded to a 2 if I rounded that. And so, but once I hit this 6, I've kind of run out of interest, right? And so keep at least 4 decimal places in general for proportions, in general. There are scenarios where if this value is really, really small, you have to keep more. So, do you remember how we wrote that interval? So we found intervals before. We want to write our interval as a lower value, comma, your upper value in round brackets. So your lower value is the 0.67 minus 0.0316, and the upper value is the 0.67 plus 0.0316. I'll just do those rounded values. Lazy. I get an interval of 0.6384 up to 0.67 plus 0.0316 up to 0.7016. You can convert these to percentages if you'd like. 63.84% to 70.16%. Would you believe me if this was only half the work? I told you it's only half the work. We've done so much. Well, we introduced a lot of concepts, but we haven't actually done a lot, right? Most of the time you would start here. So the question would say, construct a 95% confidence interval for the true proportion of American Facebook users, blah, blah, blah. I know, blah, blah, blah. It's going to come back to haunt me. Once we've calculated the confidence interval, we always have to interpret the confidence interval. And so we always need to interpret the confidence interval. What's really nice is, yes, every confidence interval that we make, and if you kind of scan ahead in the formula sheet, there's a lot of confidence intervals that we'll build, right? But all of them, we use the same interpretation, right? So as long as you memorize this interpretation, right? And I would actually prefer it if you don't stray, just because there are a lot of ways that you could misinterpret the confidence interval, okay? And so until you have that beautiful aha moment of, oh, that's what we're saying, right? I would prefer it if you just memorize it, kept saying it until you think, oh, that is true. Of course, that's true, right? But that's kind of how I would recommend doing it. What does all CIs, confidential informants, no, confidence intervals, are interpreted the same way. Is it two T's? Whatever. We are, I think there's not two T's. It just read as interpreted, and that felt weird. It's what? One T, otherwise it's interpreted. Well, the more I looked at it, interpreted, no. Okay. There's going to be some blanks depending on what the question asked you for, right? So we are some percentage. Now in our case, we built a 95% confidence interval, right? And so we are going to be 95% confident the interval from the lower value to the upper value. And it's really important that you list them from smallest to largest, right? Because an interval from 70 to 63.84 doesn't exist, right? You have to list them from smallest to largest. And so we're 95% confident that the interval from the lower value, we'll do a general interpretation first, and then we'll do a specific one for our interval. To the upper captures. Now that's going to be a really important word here. Right? If we think about fishing, right, we had that analogy of, okay, fishing with a spear versus fishing with a net. We actually don't know either way if we caught the fish, right? The fish being our population proportion, right? And so we're only 95% confident that this interval has caught our P. That's okay, right? Because of our sample, and samples move around, and maybe we have a weird sample. That happens. Okay. But this idea that we're trying to capture something that's fixed, that's important. Okay? Captures the population parameter of interest. Now this part, the population parameter of interest, what you're going to do is you're going to rephrase the question as an answer. And so here, rephrase the question as an answer. No? It's going to take some work, right? Memorize it, do whatever you need to do, but I don't want to see any fancy takes on your interpretation, right? I would prefer to just see this regurgitated confidence interval interpretation until you feel confident in what you're saying, right? Which is okay if it is for the final exam, right? It's going to take a lot of time. I can't remember if I've told you guys already, but it wasn't until I was studying for the final exam, so that's where I got that from, that I was like, oh, I see. Until then, I just kind of memorized it and just kind of, you know, gone through the motions and managed. And so it wasn't until I was studying and for the final exam, which sounds bad, but I'm happy, it worked out for me. And so that I had that kind of aha moment. And so it's okay if it takes some time, right? But I want you to have proper building blocks. Okay, so don't try to make something fancy. Most likely it will be inaccurate, which, as you just learned, is a huge pet peeve of mine, right? Can't say anything that's false. So for our interval, this little guy, I'll just copy it so I have it. To interpret this interval, right, we use the same setup. We're 95% confident because we built a 95% confidence interval. We are 95% confident the interval from 0.6384 to 0.7016 captures what? Well, whatever we were told to estimate in the question. Right? And so I'm going to take this, it's a long ways, quite a long ways ago. Captures, paste, and I'll just move it here. Captures the true proportion of American Facebook users who think Facebook categorizes their interests accurately. Right. We already said that the true proportion, and I'll finish this off here, is P, right? And so here, we want to say captures the population parameter of interest, right? Or just the parameter of interest. But I want to emphasize that it has to be for the population, right? And so the true proportion is the population proportion, huh? P. And so now what we're really saying is that based off of my sample, right, I'm 95% confident that this interval captures the population proportion. It's really important to remember that this population proportion is fixed. It exists, right? All Facebook or all American Facebook users exist. And if they were presented with a list of categories that should represent them, they can say, yes, that represents me, or no, it doesn't, right? And so it is out there, we just don't know what it is, right? And so that's why we're only 95% confident, right? And we're trying to capture this thing. Yeah? Okay, nice. So once you've constructed your confidence interval, you have to interpret the confidence interval. Usually for confidence intervals, I make them 4 marks, which means I give 2 marks for the math, right? Easy enough. And I give 2 marks for the interpretation, right? Which is why I'm always really sad when I don't see an interpretation, because that's 2 marks off, right? But that's the tricky part about this course, right? Is I've said it before. It's this dance between math and kind of an English style course, right? And so yeah, we do some math, not hard math, but we do some math. But then we have to interpret it, right? And we have to interpret it properly, right? And so hence the split. Hence the split in marks. Huh? The question will say interpret the interval, so you don't have to remember, but lots of people miss it. Huh? Oh, any questions? Hopefully you would have stopped me. Here's all that same work that we did neatly on one slide, but I talked a lot around it. So, really, when we're saying 95% confident, what we are theoretically saying is if we took many samples, right, each one would have a p-hat, each one would have its own sample proportion, right? Even if they were the same sample size, the p-hat would move around, right? Which means that your interval around your p-hat would also move around, right? And so if we took many, many, many of those, then about 95% of those intervals would contain the true population proportion p. So there's a chance that even if we sampled randomly and we have enough successes and failures, right, all those conditions are met, there's some probability, a 5% chance, right, that we just have a bad sample that we're using. But we don't know that. Little cartoon. The width of an interval. So remember in the interval, we have our Z star, which determines the width of the interval, right, or our confidence level. Okay. So if we want to be more certain that we capture the population parameter, right, so we want to increase our confidence level, right, 95, not 95% confident. What if I want to be 99% confident? Should we use a wider interval or a smaller interval? Well, we should use a wider interval. And you have to sit down here, I think. Oh, this though. Like I change it every day. I should just start down here, I guess. No, that's too boring. Okay. Look at tomorrow's weather. The high temperature will be between 40 below zero and 200 above in Fahrenheit. That's true, probably, because that's all the temperatures, right? But it's not very informative, okay? And so if the interval is too wide, right, then it may not be very informative. I did have a student one time ask me, why don't we do a 100% confidence interval? So now I'm going to throw that back to you, right? Why wouldn't we do a 100% confidence interval? Be awesome, right? I'm 100% confident, right? And so, but what would we need to do? Remember, for our 95% confidence interval, right, our Z, our negative Z star was out here, and our Z star negative 1.96 and 1.96. If I wanted to push this out, make it wider to 100%, right, 100% would be out here at negative Z star would be negative infinity, and positive Z star must be infinity. Telling someone, well, I'm 100% confident that it's somewhere between negative infinity and positive infinity, just isn't going to cut it, right? And so the trade-off that's been decided between confidence and precision is 95% as a default. So here I'll just add a note. So the default confidence level is 95%, as it is considered a trade-off between kind of a reasonable confidence, right, and precision. As it is considered a reasonable trade-off between confidence and precision. So that's the problem with going too wide on your confidence interval. Now we've already seen how we find the Z star. Oh, before I say anything else, how about a new table? I've got some hole punched ones if you prefer, but I'll leave them up here and then I'll send the other ones around. So if you prefer a hole punched version, they're up here. Otherwise, grab one of these, pass it down. A new table, isn't that so exciting? Wow, big day. Just before the, trade-off or Trello. Bang on. So those tables are making their way around. That's good. So we saw the hard way of finding the Z star. You know how to do it, right? And so that's nice. But we're going to have an easier way for finding the Z star. And so some commonly used confidence intervals, we use 90, 95, 98, or 99% confidence intervals most of the time. I even tend to stick to 90, 95, 99, boring. And I used to have to memorize the Z values, if you can believe that, back in my day, but now I just give you the table. So the table, did everyone get one? Did we run out? This whole section doesn't. Did you get one? Yep. It's on Google if you want. And then some luckies are gonna get the whole bunch. So if you don't have one, grab a whole bunch. They're only defaced a little bit, the whole bunch. Right. So the table that's making the rounds is at the kind of the next page of the tables posted on Moodle. So if you want to have a PDF version, right, then it's there. And it looks like this. It's called Table C, the T distribution. Oh, what? We were just getting a handle on the Z distribution. We're going to hang out in Z for a little bit longer, right? And so what I am asking you to do is just ignore most of it for now. Okay? And so, but there's a method to my madness. Notice that this looks very similar to the distributions that we're used to seeing, right? Now, we do have this very enticing confidence level up at the top. That looks promising, right? And because we know what our Z star should be for a 95% confidence interval, right, let's confirm. So ignoring all of this because we're not working with the T distribution, but a little fun fact, the T distribution eventually turns into the Z distribution. Wow. So here we are at a Z star. So for now, we're only paying attention to these two lines and jumping all the way down here. to find that Z star value. It's only a little bit quicker. You know how to use the Z table. So if you prefer to use the Z table like we did earlier, where we said, okay, I want a 95, I want to force 95 in the middle, then I have 5% split in half in the tail, and then you can map it back. You're allowed to do that, right? Or you're also allowed to use this table. Now I've got a little convenient crop top of the table. So here, this is our first time seeing this new table C, and notice that I've cropped most of it out. The degrees of freedom. All right, we'll get there. But for now, we're just going to work with the confidence level and the Z star. Notice that this, so I'm going to call this the T table most of the time because it's the T distribution. And so in the T table, we get 3 decimal places as opposed to 2 decimal places, right? And so here we get a Z at 3 decimal places, whereas our Z table only gave us 2. That's okay, right? And so we can confirm, right, that for a 95% confidence interval, our Z star should be 1.96. Right? But now if I said, hey, why don't we go ahead and make a 99% confidence interval, right? Now, right, that was probably the hardest part earlier, was trying to figure out what your Z star is. And now for a 95 or 99% confidence interval, you would use a Z star of 2.576. Right? Notice also that Z star is increasing as you move out, right? It's the equivalent of moving out towards infinity, right? And if you want to get really crazy with it, this one-sided P is the one-sided probability, right? The area in one of the tails from a Z of 1.96, which is what we used to find 1.96 earlier. Right? So it's all there, just in a different format. Okay? So it makes sense as your Z moves out further into the tail, then what's happening to the area in the tail? It's getting smaller and smaller and smaller. Right? And so that's good to keep track of. And so, but for today, we're just using this table to find our Z stars. Now, here, she's only got 2 decimal places, but that's okay. Which of the below Z scores is the appropriate Z star when calculating a 98% confidence interval? So 98%, we're going to go here, and for 98%, I have a Z star of 2.326 or 2.33 if you want. I would be okay with you choosing C or D. Technically, the plus or the minus, it doesn't matter. I suspect that she wants you to choose C, but I'm personally okay with D because by symmetry, they do the same thing, right, as we've seen. Nice. Because we did that one, I'm going to delete it here. So in terms of setting your confidence level, right, for your confidence interval, Now, I would recommend that you use the t-table from here on out, just because you get 3 decimal places instead of 2, and once you get used to using this table, this new table, right, it's actually easier to use, right? Oh, that's what I wanted to say. Notice how there are only positive versions of the z, right? But that's because by symmetry, right, it behaves the same on the negative end, right? So we really only need to know what the positive values look like, right? And there are a lot of Z tables out there that only give you the positive values, right? And then you, by symmetry, know what the negative values look like. To save some space, guess I can squish this up here. Confidence intervals are always about the population. It's really important that you're talking about the population because you're 100% confident about the sample proportion. It's your sample. You know everything that you could possibly want to know about your sample, right? And so that's why you always want to make sure that you're talking about the population. So here, since we know everything about the sample, right? Anything you might want to learn, you have a sample, you can use it. So that's not important, right? It's about the population. Confidence intervals are not probability statements. Okay, that's the one that people love to incorporate, right? The probability is this. No, you're 95% confident that you've captured the population proportion. And so they're only about population parameters such as p or mu later on, right? Not individual observations. And they're really only reliable if your p hat, for example, they're based on is an unbiased estimator of the population parameter. What this is really saying is if the conditions for inference are satisfied. So that's why we have to check the conditions. I'll delete this one too. Now, we've talked about this earlier, but there is this little graphic that I think makes it a little bit easier. But if you took many samples, right, we understand that if I take a new random sample of American Facebook users, 850 of them still, I would find a slightly different p hat, right? Might not be 0.67, it might be 0.665. Wow, crazy, or something like that, right? And so our p hat moves around depending on our sample, right? And so that's indicated by these little dots here. All right, and so here I have my sample proportion. Here I have a different sample proportion. And a different sample proportion, and they can move around, right? And remembering from our confidence interval, plus minus p hat plus minus z star times p hat q hat over n. Well, n is staying the same for each of these. My p hat keeps changing, right? My q hat is 1 minus p hat, and I'm still building the same confidence level. And so really, I'm going to have kind of this buffer moving around as well. Now, out of 25 different samples, right, 24 of them will capture this population proportion is at this faint line here. So here, this population proportion exists. We don't know what it is. And so 95% of these confidence intervals will capture the P, right? But the problem you want to say 95% confident is because you don't know if your P hat is one of these baddies, right? Even with proper sampling and things like that, right? Just because of variability in the population, right? And so, yes, 95% of them capture the population proportion, but 5% don't, right? And you don't know which one is yours, right? I have to. But any questions about the confidence intervals before we get going? So I just want to introduce hypothesis testing because it's a really big concept. Okay, so I want to kind of get a head start. I know, rude. I know. Hypothesis testing. Well, let's start here. I abbreviate it HT because again, it's really annoying to write. And hypothesis testing for one sample proportion. This is where we introduce the rules of hypothesis testing, and don't worry, there are many of them. And so that's why I need to get a head start. But I don't know why it says remember when. Never seen this example before, but I think given this little blurb, it's called Gender Discrimination Experiment. I think I've read about it, and it was done in the 60s or something. But anyways, we've got the gender of some employee, right? And whether they were promoted or not promoted, right? And so we have a sample of 24 males and 24 females, and 21 of those males were promoted and 14 of those females were promoted. Okay? So we can have some sample proportion of males, right? 21 out of 24 males were promoted, right? 0.88. And we can have a sample proportion of females who were promoted, 14 out of 24, right? Which is also why we had to practice being able to read contingency tables, right? Because often this is how we summarize information, and this is how I'll give you information, right? And so there are two possible explanations here, right, in terms of what we're seeing, okay? But if I had to guess, your gut reaction is, whoa, there's a difference in the proportions being promoted, right? 0.58 is quite different from 0.88, right? But there's a chance that we're wrong, and maybe they're the same, and maybe we just have a weird sample, just like we saw earlier, right? That's it. There's a chance. Okay? So some possible explanations. Promotion and gender are independent of each other, right? And so there's no gender discrimination, and the observed difference in proportions is simply due to chance, right? You got a weird group of 24 and 24, right? If you collected a new sample, these numbers would end up being much more similar to each other, right? And we just got a weird group. That's one explanation. Okay? This is what we call our null hypothesis. And so the null hypothesis says nothing is going on here. So null hypothesis says nothing is happening here. Another possible explanation of what's happening here is that promotion and gender are dependent, right? Whether you're promoted or not depends on your gender. And so what we would kind of leapfrog to is that there is gender discrimination, right? And which means that the observed difference in proportions is not due to chance. Okay? Now, this is what we call our alternative hypothesis. Okay? And so this is our alternative hypothesis. We'll always have these two competing claims, okay, in hypothesis testing. And so how we conduct our testing, though, is we start out and we assume the null hypothesis is true. And so in hypothesis testing, I'll add a page here. It's important. So in hypothesis testing, we always assume the null hypothesis. Null means zero, right? So zero change, nothing is happening here. So the null hypothesis is true until we find evidence suggesting otherwise. Right? Until we find evidence which is going to result in a probability, foreshadowing here, that evidence is going to be a probability. Probabilities are what? Probabilities are areas under the curve. Right? We've seen that before. We've done a lot of work finding probabilities, right? And this is the reason. So probability is an area under the curve. So we assume the null hypothesis is true until we find evidence or find some probability that's too small, right? Or just evidence in general against the null hypothesis. In which case we reject the null hypothesis in favor of the alternative hypothesis. It's going to be the longest run-on sentence you've ever seen. In which case we reject the null hypothesis in favor of the alternative hypothesis. In terms of this example, right, we would go through and we would say, fine, let's assume that promotion and gender are independent. I assume that 0.88 is basically the same as 0.58 until I do some math, secret math, yeah, until next day. And I say, hey, the probability of these two things being the same is very small. Then I can reject the null hypothesis in favor of the alternative. And then I can say, hey, promotion and gender, they're dependent on each other. Right? But I'll leave you with that little tidbit for Thursday. If you have any questions, let me know. Otherwise, I'll see you then. Were there any spare tea tables left over?
Yeah.
Yep. I'll stop this recording so it's not just empty space.